In this video, I'm going to explain the design of cooler. Uh, Design of cooler, heat exchanger, and heater are quite similar. Only difference is like in heat exchanger, there are two process streams involved, like hot and cold process streams, and there is heat transfer between these two. In cooler, there is cooling utility involved, like cooling water. In heater, heating utility is involved, like indicated from its name. Uh, for example, steam or hot water. So let's start with this example where gaseous stream is basically cooled from 800 degrees Celsius to 1400 degrees Celsius with the help of boiler feed water, which enters as a liquid at 25 degrees Celsius and leaves at 600 degrees Celsius. So boiler feed water is basically at 5.7 atm, and the corresponding saturation temperature is 157 degrees Celsius, which you can determine from steam table. So what happens is basically liquid water is basically heated from 25 degrees Celsius to 157 degrees Celsius with the help of sensible heat given by the gaseous stream, and then there is phase change at 157 degrees Celsius uh, as with latent heat, and then there is superheating of steam from 157 degrees Celsius to 600 degrees Celsius. So no matter what is the type of exchanger, cooler or heater, first step is to calculate the heat duty. So for that, formula is Q is equal to mCp delta T, where m is flow rate of stream, that is gas here. Cp is specific heat capacity, delta T is temperature difference, which is 800 degrees Celsius minus 40 degrees Celsius, which comes out to be 760 degrees Celsius. So once you substitute the values here, you obtain the heat duty as 16.8 kilowatt, or when you convert it into other units like BTU per hour, it becomes 57,232.986 BTU per hour. Then next step is to calculate the mass flow rate of boiler feed water, which is required in order to cool the gaseous stream from 800 degrees Celsius to 40 degrees Celsius. So with the help of this heat duty we just calculated in previous step, we can determine the boiler feed water. Formula is same, Q is equal to mCp delta T. So by rearranging, we have here heat duty. This is basically sensible heat, which we previously discussed. This is latent heat. This is again sensible heat for vapor region. So it is from 25 degrees Celsius to 157 degrees Celsius it is heated. Then there is latent heat, and then there is heating of vapors from 157 to 600 degrees Celsius. So we obtain boiler feed water flow rate as 17.2 kg per hour. Next step is to calculate the physical property data. So we need to collect a lot of physical properties like density, viscosity, thermal conductivity. So we can either determine these physical properties using the SPAN, or we can use the different correlations that are available in literature, and with the empirical values like ABC, which are determined and specific for each component, are determined experimentally. So we have physical properties here for both gaseous stream and boiler feed water. So next step is to calculate the log mean temperature difference. So we have here hot water, hot stream inlet minus cold stream inlet, hot stream outlet minus cold stream outlet. So in this way we determine the log mean temperature difference as 71.42 Kelvin. After that, we need to determine the inner pipe heat transfer coefficient. So for that, we have taken the inner pipe diameter as 2.067 inches. So we have converted it into feet by dividing it 12. So we have determined the flow area as 0.0233 feet square. So now we can determine the mass velocity by dividing the flow rate by area. So we have obtained it as 563.12 pounds per hour into feet square. So next step is to calculate the Reynolds number, so which is D into mass velocity divided by viscosity. So we know each and every value. So after substituting these values, we obtain the Reynolds number as 2490.3. So using this Reynolds number, we can find the heat transfer factor from this figure, like 2490 from here, and in this way this heat transfer factor is obtained as 30. Now next step is to calculate the Prandtl number, which purely depends upon the physical properties like mu, c over k. So we know all of these physical properties, and you know why I mentioned that we need to calculate the physical properties in the start, because these are required throughout the design. So after that we can find the inner pipe heat transfer coefficient using this formula, and we can neglect this viscosity correction because this is very small normally. So we have this heat transfer factor, thermal conductivity, diameter, and this Prandtl number. So after substituting the values, we can obtain the value of inner pipe heat transfer coefficient as 28.04 BTU per hour feet square into degree Fahrenheit. After that we need to calculate the heat transfer coefficient for outer pipe. So first we need to calculate the flow area for the outer pipe, which is basically pi by 4 outer pipe diameter square minus inner pipe diameter square. So we obtain the flow area as 0.0204 feet square. Again we need to find the mass velocity, which is determined again by dividing the mass flow rate divided by flow area. So it comes out to be 1858.8. So then we need to find the equivalent diameter, that is outer pipe diameter square minus inner pipe diameter square divided by inner pipe diameter. So it comes out to be 0.1312 feet. Then again we need to find the Reynolds number, and then using this Reynolds number we can find the heat transfer factor, that comes out to be 50. Again we need to find the Prandtl number, because we need this Prandtl number in heat transfer coefficient for outer pipe diameter, outer pipe heat transfer coefficient. So we just need to substitute these values. Again we can neglect the viscosity correction. So substituting these values, we obtain the outer pipe heat transfer coefficient as 6.314 BTU per hour into feet square into degree Fahrenheit. Then we need to find the overall heat transfer coefficient. So for clean overall heat transfer coefficient, we have this equation, that is in denominator we have a product of outer and inner pipe heat transfer coefficient, and in denominator we have sum of both of these values. So we obtain it as 5.14 BTU per hour into feet square into degree Fahrenheit. Then since we know that there is fouling in heat exchangers, so we need to account that fouling during in design as well. So this fouling factor is taken as 0.03. So after substituting these values, we finally obtain the design overall heat transfer coefficient as 5.08 BTU per hour feet square into degree Fahrenheit. So now we need to determine the heat transfer area, which is determined using the design equation, that is Q is equal to UA delta T. So rearranging, we get this equation. We have all of these parameters: heat duty, design coefficient, over log mean temperature difference. So substituting these values, we obtain the heat transfer area as 87.77 feet square. So now all of the previous steps were for double pipe heat exchanger, because this area is basically less than 200 feet square. So if area is greater than 200 feet square, then double shell and tube heat exchanger is better option, uh, because it is optimal for design and for from economics point of view. So now we need to find how many hairpins we need for heat exchanger. So for that we can find the external surface, so which is basically pi into diameter, that is inches, and we divide it by 12 to convert it into feet. So we have overall heat transfer area, and we have external surface per linear feet. So from there we can find the required length which is needed for this much duty. So it comes out to be 140.88 feet square feet, sorry. And then we, for number of hairpins, we have taken length of one hairpin as 20 feet. So when we divide total length by 20, we obtain 7. So it means that we need 7 hairpins, like 7 double pipe heat exchangers that work in series for this heat duty. So in the next step we need to find the pressure drop on inner pipe and outer pipe. So let's start with the inner pipe pressure drop. So since Reynolds number is quite low, so we can find the friction factor using this formula, that is 16 by Reynolds number. So substituting these values, we obtain the friction factor as 0.00642. Then we can find the head loss in the inner pipe, and we are given this formula. We just need to substitute these values. So after that we obtain it as 27.57 feet. So for pressure drop we can find it as we need to multiply the head loss with the density, and then there is a unit conversion from feet square into inch square. That's why we divided it by 144. So it becomes pressure drop in uh, pounds per square inch. So there is a limit of 10 psi that is allowable. So our pressure drop is quite less than the allowable limit. Then we need to find the pressure drop in annulus area. So equivalent diameter, hydraulic equivalent diameter is basically difference between outer pipe and inner pipe, which is basically flow area. So from there we obtain it as 0.0573 feet. Then we need to find the Reynolds number, because equivalent diameter change from the heat transfer area, heat transfer equivalent diameter. So that's why we obtain it as 3610.5. So now friction factor is determined using this equation, since Reynolds number is high. So that's why this equation for friction factor is changed. So after substituting these values we obtain it as 0.01164. So again formula is same for head loss, we just need to substitute the values, and we obtain it as 8.4 feet, sorry. So then for head loss we just again need to multiply it with the density, and there is unit conversion, and we obtain it as 0.0116 psi, which is again quite less than the allowable limit. Now once we are done with the design, we can find the cost of the heat exchanger. So for the costing of heat exchanger, we have a general equation to find the purchased cost at the ambient temperature and pressure. But here you can see K1, K2 and K3. These are equipment specific. Like for double pipe these values will be these. For shell and tube these values will change. Here A is the sizing parameter, which is basically area of the heat exchanger, which is 8.15 meter square in this case. So we just need to substitute these values and we will be obtaining the purchase cost at the ambient conditions as is. For bare module cost, we need to counter for material of construction and pressure factor as well. So we have taken carbon steel as material of construction for heat exchanger. So for carbon steel, FM is 1, that is material factor. This pressure factor is also 1 because our operating pressure is quite less than the limit, so we don't need any special treatment in the material, so that's why it is 1. B1 and B2 are empirical constants, so these are values for shell and for double pipe heat exchanger. After substituting these values, we obtain bare module cost as 11817.4. But keep in mind that this bare module cost is in 2001, I think. So we need to convert this bare module cost into your current year, like 2023. Okay, so that's all.